Any of you ever hear concerns that maybe your system is too slow to boot? And oh, wow. Well, this is all about a tool that's in the open source on what is normally called TIANF Core that can be useful in, and we find it useful, in measuring the components of what it is that makes your system or driver slow. The package in the open source is called Performance Package. We're going to talk about how it works. We're going to give some examples that are tuned to different sorts of use cases. And we're going to talk about what might be done if you're an IHV that doesn't build platforms. The Performance Package is part of EDK2. If you're not using EDK2 to build your drivers, then you're sort of not really part of this conversation. It inserts what you would call low overhead software measurement start and stop hooks into a driver, into a UEFI driver. And this can be a PEI driver, usually called a PEIM, or Dixie driver, which is what we're going to talk about today. And it could indeed be an option ROM, or it could be used in a bootloader or any other kind of UEFI application if you saw a use for it. The duration measurements, the time between the start and the stop, are based off of a high accuracy CPU timer. So there is a little bit of a hardware dependency on the system that it's running in. The measurements are stored in a central buffer, and there's a tool called dp.efi to display the results. So let's look at this in a little more detail. There's a library called Dixie Core Performance Lib, which is the central collector of the performance measurements. It grabs the pre-Dixie measurements from a hop, that arrow on the left, and then each driver connects to this core library via a protocol call. The information from the driver is stored in the in-memory database, and it can be retrieved by the EFI tool. So what do these look like in the source? The typical way is to insert one of these macros, which is either perf start or perf start EX. The parameters of the macro include identification of the measurement that's being taken. The identification consists of a handle. So for example, if you had multiple devices that were being controlled by the same driver, they would each have a handle to that device, so you could distinguish between the different instances of this driver's execution. The token and module are just sort of strings that you supply. The timestamp is a caller passed start time, which isn't normally used except in a special circumstance. Identifier is sort of an extra sort of class that can group. For example, TPM might be a class where you could group all of your TPM related measurements into one class. So perf start EX is followed by perf end EX, which passes the same information. And here's what it looks like in source. An example from the open source Dixie main. We're going to measure the time of core initialized dispatcher. And so we have a perf start and a perf end. Later, we can see the output in dp.efi, the number of microseconds that core initialized dispatcher took. So if you're looking for places to optimize, this helps you zero in. Now, I mentioned that perf start, perf end are low overhead, and they really do try to exclude the overhead from the measurement. Okay? But if you nest them, if, for example, if there were additional perf starts inside core initialize, you know, the wrapper measurement's going to include the overhead, and the overhead consists of taking the measurement information and finding the right spot in the buffer for it, potentially growing the buffer. So you have to take that into account when you're, if you, for example, measured all of Dixie, you're going to have some, and you had a lot of measurements inside of that, it's going to be a little bit higher than it would be otherwise. The macros go into the source. Obviously, there's some overhead. We don't want them there in a production build. So there's a PCD that if you turn that 1 to a 0, then the macros are 0 overhead. Now, PCD, of course, shows up in the build DSC file. So you have essentially the capability of having a perf on build and a perf off build for the same source files. Here we have a sort of a real world BIOS kind of problem here. The engineer's looking at this. Somebody says it's booting slowly, and my goodness, yes, 19 seconds to boot. That is kind of slow, right? It just so happens that the answer to the question of why is on the first line of the output. And I didn't really plan that. That's where it is. You can see that of the 19 seconds, 14 of it is taken up by this one driver. So it's clear that you're going to have to delve into Hecky-Dixie to figure out what's wrong. And obviously what's wrong here is that the ME is frozen, needs to be reset. There's some sort of mismatch between this driver and the hardware. So that's the kind of thing of helping you debug a problem. In terms of optimization, there's some other items in the output from DP that can show you in particular cumulative categories. And you can see where the big blocks of time are spent. For example, load image, which is bringing the drivers in from the storage medium, that's really not all that expensive. Start image is where all the time is taken. So the way that the start image measurement is accomplished is that DP has these cumulative categories, which say in your output, lump all of the measurements, add them all together that have this token category, this type. And this might be useful if you were doing some sort of a network application and you wanted to see all of the time spent in TCP/IP or all of the time spent in the network driver. You would, however, need to modify the source to the dp.c to add your own cumulative category. So you can customize DP to give you the kind of output that will help you analyze your problem. So I mentioned that PCD, and it controls the library that was added to Dixie main, where the performance protocol really works. So some of us are BIOS vendors, and we do system builds all the time, and it's pretty easy for us to do perf on, perf off. And I started thinking about, what about people who aren't IBVs? Is this a tool that they might be able to use? Well, you're probably testing on some platform, but what if there's no perf build for that platform? Obviously, if it's a retail platform, the perf macros are going to be shut off. It's going to be really not going to be very useful. You might have Harry on speed dial, and you could say, Harry, I need a perf build for XYZ. And a couple days later, you're all set. But what if you wanted to be more of a do-it-yourselfer? I started thinking about, I really didn't know the answer to this in preparing this presentation. I started thinking about, what would it take if an IHV wanted to just measure his driver, wanted to use this perf capability, independent on any system? So the goal that I set for myself was an IHV kind of test. You're going to boot to the shell. You're going to start the perf package somehow. And then you're going to have an instrumented IHV driver that you're going to test via whatever test procedure you have in the shell. Network driver, maybe you're going to do a download. I didn't think anyone had done this before. Maybe they have. I wrote this thing, and it turned out to be, at least the C file is pretty simple. I wrote this file called perfdixie.c, and that's all it turned out to have. But really, that's probably not going to teach you very much, because that's not where the secret is. Oh, so probably the secret's in the INF file, right? So here's the INF file I wrote, and you can see that we're including the performance lib there at the bottom, but really that's not so interesting either. There's really not much secret there. Perfdixie, this is the thing I want to load at the shell. What's the key to making this work? The first key is in the DSC that I used to build perfdixie. So in an EDK2 DSC, you have this little trick that you can do. With these brackets, these braces, you can override the context of the rest of the DSC, and you can have a specific settings for building your driver. So the first interesting thing that I did was I overrode performance lib with Dixie core performance lib. Now, you don't need to do this if Dixie core is already built with performance lib. You're fine, but what if it isn't? This is a way to put that Dixie core performance lib into a loadable driver. And then the second thing I did was I turned on the property for the perf. And the magic is all in the constructor of Dixie core performance lib. Remember, in the C file, we didn't do anything. We didn't have to call anything magic. But EDK2 has this phenomena called library constructors. And the library constructor gets called every time the library it gets called by the EDK2 module startup, the hidden C file that is created when you build your driver. What it does before it enters your entry point is it calls the constructor of every library that you've embedded in your module. And that constructor for Dixie core performance lib sets up the in-memory database. To build it, it's pretty simple. I added this perfdixie to the performance package. And you can see I added it in the components and built that package. And out comes my tool for starting performance package from the EFI shell. So here's the final version of perfdixie.c. And you can see we've added a little bit in here. We're doing a perf start, a set timer, wait for event, and then an end. And I call this the calibrate code. We can see in the output, we can see that the calibrate was 99% accurate. So you can get an idea of the accuracy of kind of verifies that you're using the correct timer, and that remember in the C code, the number of zeros there on set timer might throw you off because it's in tens of, that's 1 second. And here we see that it came out 0.9919 seconds. The second entry was another driver that was loaded and tested from the shell. And it didn't really do very much. The output's recorded in dp.exe. What do we take away from this? Performance package can be really useful, diagnosing problems in a system boot, and it is a tool that can be leveraged for the IHV. And taking a look at the source might show you some tricks about EDK2 that you haven't previously worked with. Yeah, I did attach the source files, and I assume they'll be posted along with the PDF. Any questions about how EDK2 works, how performance package works? The question was, are we going to check it into Tiano Core? You know, my initial thing was I would leave it as something useful to people that read my PDF, but sure. Would it work with a...
For the ARM64-bit platform, if I were to compile for that, or would I have to implement some assembly code?
We're going to have to look at the INF file. The INF file and the DSC file specify timer lib. And you can see that I'm using performance package library TSC timer lib, right, which is checked in. And if you take a look at that library and your platform does not happen to be constructed in a way that timer is at that place, you would need to override this timer lib by a alternative timer lib of your own construction. You know, there is a timer lib in your build for ARM. This is the same timer lib that's used other places, right? You already have the correct timer lib, is what I'm saying, if you have an ARM source build, right?
For the platform.
For the platform, right? And this is not a magical timer lib. The reason that it's in performance lib in the open source is that the open source doesn't have a lot of platform packages, right? So essentially in an ARM situation, you would want to replace that timer lib with the one that you developed in order to port to that system. Yes, and Mark reminds me that if someone wanted to suggest, we could check that in. I wouldn't be surprised if it was already in the open source in a different spot. But your assumption is correct. The one that is checked in today into Dixie Core Performance Lib is kind of a universal x86 version.